Isomerism is the existence of different compounds having the same molecular formula but different structural formula or their arrangement in space. And this phenomenon can give rise to them having different physical and chemical properties. Now, we have two types of isomerism. We have the structural isomerism, and then we have the stereoisomerism. So with that being said, these are the two classifications of isomerism. We would start with structural isomerism. Structural isomerism can occur in the same homologous series or different homologous series for a particular member. This is what I mean. If we have an alkane as one homologous series, and then we have, let's say, an alkanone, then we have, let's say, an aldehyde or alkanal. So you see, now structural isomerism can occur when there's a particular or two members in a particular homologous series, that is alkane, can exhibit structural isomerism. Then we have other members from different homologous series can also exhibit structural isomerism. Now I will use an example so that you understand better what I mean. If we have let's say we have butane, CH3, CH2, CH2, CH3. This is butane, right? Then let's say we have let's say 2-methylpropane, that's CH. Then we have methyl here. Then we have CH3. Now, these are two isomers. This is one isomer. These are isomers, okay? And why are they isomers? Because they have the same molecular formula but different structural formula. What's their molecular formula? How many carbons? 1, 2, 3, 4. This is C4H10, right? This is also C4. 1, 2, 3, 4. 4 hydrogens. Add up the hydrogens, add up the carbon and hydrogens, you also get C4H10. So that makes them structural isomers. As you can see, same member in a homologous series alkane can exhibit structural isomerism. Then we can also have from different homologous series, that's different family. Okay, let's look at an alkanone and an alkanal in this case, all right, where structural isomerism also exists. So let's take a look at this compound, which is an alkanone. Let's say this is H3C. All right, then this is CH3. As you can see, this is an alkanone because it has the functional group RCOR, right? So this is a functional group, right? So this is an alkanone, and the alkanone is known as propanone. This is a propanone. Now let's find its isomer, which could be an alkanal, and then if we should have, let's say, CH3, CH2, CHO, or make it more elaborate. Let's expand this. Let's make it like this: H3C CH2, right? Then C double bond O and H. So this is propanal. Can you see? Now these are two isomers too, because if you look at the combination, sorry, I didn't write this thing very well. This is supposed to be where is it? It's supposed to be C. This is H over here, right? So how many carbons do we have in the propanone? That's this compound. We have 1, 2, 3. We have 3 carbon, 6 hydrogens, 3 carbon, C3H6, and 1 oxygen, right? So in the propanol, how many do we have? We also have C3, H6, okay, then 1O. Can you see they have the same molecular formula, but if you observe their structure, they look structurally different. So they are also structural isomers, all right, resulting from different homologous series, while these other one results from same homologous series. Now we also have some other subtypes of structural isomerism, which we've just laid background for. We have what is called chain isomerism or chain isomers, okay, and then we have positional isomerism, okay. So we're going to discuss these two right now. Now, chain isomerism results for the same compounds in the same homologous series whose functional groups, all right, whose functional groups are at the same position. So that is chain isomerism. When these compounds have their functional groups at the same position. Now let me try to find an example. Let's say pentanol, CH3, CH3, CH2, 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 1, 2, 3, 4, 5. This is the fifth one. Then with an OH. Can you see that? So let me make this more clear. This is CH2OH. So this is pentanol, right? Can you see the position of the OH? Now note this position, because chain isomerism actually states that the functional group has to be on the same position for the isomers. Now let's look at this other structure, CH3, CH2, let's say CH, right? Then we have CH2, let's say this is OH. And then here, over here, we have CH3. Now, if you look closely, these are isomers because they have the same molecular formula. Check the number of carbon, 5 carbons here, 1, 2, 3, 4, 5, 5 carbons here. How many hydrogens? This is 2 plus 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's C5H12O. All right, can you see that? So this is also 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like, yeah. So this is their molecular formula, but if you look at them structurally, they are different. The first one is 1, 2, 3, 4, 5. It's a pentanol. So I can have here, this is pentanol, which is a chain isomer of, this is 1, 1, 2, 2 methyl, 1, 2, 3, 4 butanol. So this 2 methyl butanol, which is also an isomer of pentanol. Can you see that? Now, this chain isomerism is said to occur once their functional groups are at the same position. Can you see? The OH is at the terminal end. That says that this is, a chain isomer because their functional groups are at the same position. That makes them chain isomers. So now let's look at positional isomerism. Positional isomerism is actually the opposite, okay? Take for example, let's say we have CH3. This is for positional isomerism. This CH2, let's say we have OH here, right? Then let's have another compound. Okay, let me just write it just below it. Let's say we have CH3 here. Then let's say we have CH, then OH, okay? Then let's say we have let's put CH2 here. Then let's say we have CH3, okay? Now look closely. Are they isomers in the first place? Do they have the same molecular formula? Let's see. This is 1 carbon, 2, 3. Okay, I think I missed one. Okay, let me correct this. Just a minute. So, need to correct this. So this is going to be CH2 because I'm working with butanol. All right. So how many carbons do we have? We have 1, 2, 3, 4. 4 carbon, right? That is C4. Then how many hydrogens? 3 plus 2, 5 plus 2, 7. 7 plus 2, 9 plus 1 hydrogen here, 10. H10. Well, then we have 1 oxygen, right? So check this one. 1 carbon, 2 carbon, 3 carbon, 4 carbon, the same thing, C4. 3 plus 2, 5, 6, 7, 8, 9. So we have same and oxygen. Can you see? They have the same molecular formula, but their structures are different. Now look at the positions of the functional group. Can you see? One is at the terminal. Here, the hydroxy group is at the second carbon, if you look closely here, but here is on the first carbon. All right. So you see that gives rise to what we call positional isomerism. Chain isomerism occurs when they are on the same position, as we've explained here, between pentanol and 2-methyl butanol. All right. So, and let's move on. So we have one other classification I omitted here. We also have functional isomerism as part of structural isomerism. Okay, so in structural isomerism, these compounds tend to have the same molecular formula. You know, there is always same molecular formula, same molecular formula, but this time different functional groups. All right. In this case, they have same molecular formula but different functional groups, resulting in compounds, belonging to different homologous series. So I'll just give an example so that you understand what I mean. So let's say we have ethanol, for example, CH3, CH2, OH. All right. Then we say we have ether. Ether is CH3, O, and CH3. Now look closely. We have how many carbons here? 3 carbons. Okay, is it 2 carbons? Yeah, 2 carbons, 1 and 2. So we have C2. How many hydrogen? 3 plus 2, 5 plus 1, 6. So I have C2H6, 1 oxygen. Can you see? Now if you look, 2 carbons, C2, 3 plus 3, 6. Then we have this oxygen. See, the same molecular formula, but different functional group. One is an alcohol, the other is an ether. So you see, this is an alcohol, all right? Why this one is an ether? That's ROR. Can you see that? So this gives rise to what we call functional group isomerism. So because these isomers have different functional group but the same molecular formula, can you see that? So let's go to the last one, which is the stereoisomerism. Stereoisomerism. Okay, so in stereoisomerism, it actually occurs when these isomers have same molecular formula. Remember, there's always same molecular formula, but in this case, even their connectivity, like the interconnectivity of the atoms, are the same, right? But they tend to differ in their orientation in space. So different orientation, you understand? So just take it as maybe if you have something like this, can you see? These look very much identical, right? But different orientation, right? So if this were to be, if this letter F were to be the molecular formula, all right, in the presence of a mirror, it looks like this. See, different orientations, all right? So that's basically it. So when these compounds or isomers have the same molecular formula and interconnection of atoms, but tend to differ in their spatial orientation, we say that that's a stereoisomer. So basically, we have two types: geoisomers or geometric isomerism, and then we have optical isomerism. Now, in geometric isomerism, you have to note that there is always a restricted rotation. For geometric isomers, restricted rotation. So for geometric isomers, there's restricted rotation around a double bond, right? Around a double bond or a ring. It can be a ring structure around a double bond or ring structure. All right. So I'll try to explain this using identical group compound, which we already know. Let's say we have this. Let's say we have H here. As you can see, there's a double bond over here. So there's restricted rotation in this case because just one plane, right? So if you look closely, you get to see that the chlorine, these identical groups, because the groups has to be identical, okay? When the identical groups are on the same side, you see all of them at the top, none at the bottom. So we tend to say this is a cis isomer. So that means geometric isomerism gives rise to a cis isomer. It also gives rise to a trans isomer. In this case, where you get to see that the identical groups are on the opposite sides of the double bond. So we have chlorine over here, gives rise to a trans isomer. You can see what geometric isomerism can give rise. If you look at it, they still have the same molecular formula, but different orientation in space. All right. So let's go to the next one, which is optical isomerism. Optical isomerism. Now, optical isomerism occurs in molecules that are non-superimposable. They are non-superimposable. I will explain this. All right. And then the compounds usually possess what we call a chiral carbon. Chiral carbon. All right. So when these are evident, that means it's going to undergo, or that compound could undergo optical isomerism. So it occurs in molecules that are non-superimposable mirror images. All right. So it just means that their mirror images are identical, but they cannot be placed atom to atom onto each other. Okay. So I will explain this. Let's have a structure. Let me use alamine. Alamine is 2-aminopropanolic acid. So let's have something like this. A chiral carbon contains identical groups, no, not identical groups, 4 of them around it. So let's say we have NH2 here. Then let's say we have carboxylic acid group here. Then let's say we have hydrogen over here. Then let's say we have a methyl over here. Can you see? Now, can you see that carbon, which you see here, is bonded to 4 different groups? And that is why we say carbon is chiral, because it's bonded to 4 different groups. All right. So that's a chiral carbon. Okay. So let me remove this. Then they are not superimposable because their mirror image cannot be placed side by side onto each other. Now, if we should have H2N here, then I have the carbon. Remember, we have hydrogen over here. Then we have over here, that's the carboxylic acid group, right? Then we have the methyl group over here. Like I said, this is 2-aminopropanoic acid. There are 3 carbons there. On the second carbon, which is this, there's an amino group. So that's why this is alamine. So if you see closely, they form mirror images of each other, but then you can't really place them. They can't really fit in side by side. All right, they are not superimposable, meaning their images cannot fit in side by side onto each other or atom by atom. That's what it means, okay? And because of this, they are regarded as enantiomers. And they are capable of rotating plane polarized light in different directions, left and right, negative and positive, right? So those which are able to rotate to the positive direction, we say is clockwise. Let me put clockwise here. Clockwise. And this is anti-clockwise, negative. Anti-clockwise is when they are trying to, if they're able to rotate to the right, is clockwise. To the left is anti-clockwise. So we tend to say left is L isomer, clockwise right is R isomer. So we can regard this as an R isomer, and we can regard this as an L isomer. Can you see that? And the mixture of both of them is called a racemic mixture, as they are considered optically active. That's optically active. Ability to rotate plane polarized light to the left or to the right. To the left is L isomer, and to the right the D isomer. So, and if they are rotating to the positive direction, they are said to be dextro-rotatory. If they are rotating to the negative, they are said to be levo-rotatory, dextro-rotatory. So these are the optical isomers, okay? So basically, this is what you should know about isomerism.